So now we're going to talk about waves, vocabulary, and notes. This is going to be part 2 of your notes. So electromagnetic spectrum, in the electromagnetic spectrum, these are all wavelengths of what I would call as light. They're just some of the wavelengths are too big or too short for you to be able to see with your normal eye. Now, it doesn't mean that they don't exist. They're all the same type of wave, just some of them have bigger or smaller wavelengths. Now, at the shorter end of the wavelengths, you have higher frequency, you have higher energy. Those are the ones that are considered more dangerous. On the right-hand side, we have longer wavelengths. Those are infrared, microwave, and radio waves. Those have a lower frequency and lower energy. So we're not really worried about those. So smaller wavelengths have a bigger frequency, smaller wavelengths have more energy, and the velocity of the wave is actually dependent on the medium or what the wave is going through. So light or electromagnetic waves will go through the air faster than they might go through glass. And this is why we're able to get light waves to curve, is because it'll go from one material to another. Transverse waves, these are going to be the waves that go up and down or side to side. So as the wave moves to the right, the string itself is going up and down. So that is also seen in this example here. We have the wave traveling along the slinky. The slinky goes up and down as the wave itself moves to the right. Now, if you'll notice right here, this red dot is basically going straight up and down. It's not moving right or left at all. But you can see where the wavelength is labeled, and that the wavelength itself, this part, the top of the wave, keeps moving side to side. So that is the direction of the wave, even though the actual molecules are going up and down. Now, examples of this wave are light waves and S waves. A longitudinal wave is a wave that looks like the slinky is getting compressed and then expands. So let's take a look at that. Here we have a longitudinal wave. As it moves, the slinky is getting squished and then it stretches back out as it moves to the right. So the wave travels along the slinky, making part of the slinky look compressed. The particles are going to move to the right and left while the wave also moves to the right. So examples of this are going to be sound waves and P waves, or primary earthquake waves, and we'll talk about those. So seismic waves are waves of energy that travel through the earth and are the result of an earthquake, a volcano, or an explosion. Think really big things that are going to make the ground shake. Now, P waves are the first waves that arrive after an earthquake. And the reason why is, first of all, that they get there faster. But what these videos are showing you is what kinds of materials it moves through. So P wave is primary wave. Those are the first waves that arrive. That's why it's a P. They can travel through both solids and liquids. And there's an activity that I do with my students here at the top. This is a P wave, or a longitudinal wave, going through students. On the top, it's a solid. The way that we're showing it's a solid is students have their hands on the person in front of them, and they're holding on, just like molecules and the molecular bonds between molecules in a solid is strong. So in a solid, one molecule is holding on to the molecule that's next to it. It's not going to let it go away. So when you have a P wave go through this in a solid, it's no problem. They push from one to the next, kind of like dominoes. Now, for a liquid, it's the same exact way. Here, it also goes through, but the difference is that there's a gap. There's like 5 or 6 inches of space in between each of the student's hands and the person in front of them. And the reason why that's important is because in a liquid, the molecular bonds are much weaker, but the wave is still able to pass through. So a P wave is a primary wave. The wave moves in the same direction as the molecules. For example, the wave and the people moved to the right. It is able to travel through solids and liquids. It is the first wave to arrive from an earthquake because it is faster than an S wave. And it is a type of longitudinal wave. S waves, on the other hand, are a little bit different. So S waves are a transverse wave. So as the wave moves to the right, the people have to move forwards and backwards. And so you can see in the top one, again, in a solid, the elbows are linked. That's going to represent the strong molecular bonds between molecules in a solid. And so you do have the wave able to pass through in a solid. In a liquid, however, the arms are not linked. That is to represent weaker molecular bonds. And the weaker molecular bonds mean that even though the girl on the far left in that orange jacket moves forwards, she doesn't drag anyone else with her. And so that means that S waves can only travel through solids. So in summary, an S wave is a secondary wave because it is slower. It is able to travel through solids only. The wave moves perpendicular to the movement of the molecules. So for example, the people move forwards and the wave goes to the right. It is the second wave to arrive from an earthquake because it is slower than the P wave. And it is a type of transverse wave. Then I want to show you how a seismograph works. So seismographs are kind of cool. What I want you to think of is, remember inertia. Now inertia is an object at rest will stay at rest, and an object in motion will stay in motion. So this part of the seismograph and this part of the seismograph are heavy, and they are going to hold still. They're not going to move. Then, just like if you were holding your pencil and your friend came and moved your paper, the pen will draw on the paper, but not because you moved the pencil, because you moved the paper. So because the seismograph is attached to the ground, the wheel or the thing that's getting drawn on is going to move, and the pencil will stay still, and you will be able to see just how big the earthquake is, because the bigger the earthquake is, the bigger the squiggle is going to be. So you are going to do a lab called Slinky Seismology in class. And when you're done with it, this is what the conclusion should be. First of all, what is the conclusions that can be made about the Earth's layers using seismic waves? Well, one of the layers of the Earth is liquid because S waves do not travel through it. And the other conclusion is that the layers of the Earth have different densities. And next, we're going to be talking about ionizing radiation.